Welcome to the lecture series on molecular symmetry and group theory. When I say this, there is symmetry in many places if you look around. Do you agree with me? The table you are using, the fan in the room you are sitting, everywhere you can find some sort of symmetry, isn't it? In this lecture series, we will focus on the topic molecular symmetry and group theory. This will be beneficial for our BSc chemistry students. This is Dr. Sharida Karangadan. I am here to help you with the topic. After this lecture series, you will be able to identify the point group and the symmetry of molecules. The purpose of knowing the symmetry of molecules is that once you know the symmetry of a molecule, then the powerful sets of tools of group theory will provide considerable insight into its physical and chemical properties. Most of the objects in nature possess varying degrees of symmetry. Some of them are depicted here. The wings of butterflies are identical on left and right sides. Most animals have a bilateral symmetry, which means they can be split into two matching halves. Here you can see mirror reflection of a woman, that is mirror symmetry. Likewise, there is symmetry in crystals also. You know about crystals and crystal lattices. Here in BCC lattice, that is body centered cubic lattice, you can see symmetry at corners. 1/8 of the contribution is similar at all the 8 corners. And in FCC lattice, that is face centered cubic lattice, there is symmetry at the corners as well as at the faces, though both are not similar. That is, at corners there are one type of symmetry and at the faces other type. Now, the symmetry can be said in terms of lattice, motif, crystal or unit cell. The motif is otherwise called lattice point. Now, what is meant by this lattice and a lattice point? A lattice is a periodic array of a structural unit. Lattice point is the position in the unit cell or the crystal where the probability of finding an atom or an ion is highest. In other words, the atoms or ions occupy the lattice points in a crystalline solid. If the structural units are periodically arranged in one-dimensional manner, we will get a one-dimensional lattice. If it is in 2 dimensions, then it will lead to a 2-dimensional lattice. And if the structural units are arranged in 3-dimensional manner, that will give rise to a 3-dimensional lattice. Now, let us remember some of the points that we have studied earlier about the lattice planes and how they are represented and so on. What are these lattice planes? Lattice planes are parallel equidistant planes passing through the lattice points. And these lattice planes have to be represented in some way, isn't it? So, for representing the lattice planes, we use Miller indices. And what are these Miller indices? They are sets of integers that are used to specify lattice planes. If the planar coordinates are 2a, 2b and 2c, then 2, 2, 3 are the V's coefficients. The reciprocal of the V's coefficients are known as Miller indices. Here it is 1/2, 1/2 and 1/3. When fractions cleared, it will be 3, 3 and 2. Hence, the plane is represented as 3, 3, 2 plane. Now, let us talk about symmetry of a one-dimensional lattice. As we said earlier, the periodic array of structural units in one dimension will give rise to one-dimensional lattice. That is, translation in one direction. Say, translation in x direction, it will result in a row. Here you can see the repeating unit is vector A. Coming to the two-dimensional lattice, the periodic array of structural units in 2 dimension will give rise to two-dimensional lattice. Two-dimensional translations, that is, if the translations of the unit cell occurs in 2 directions, say x and y, that will lead to a net or a plane. Here it is xy plane. And what is this unit cell? A unit cell is a repeating unit whose translation only will generate the entire pattern. Now we can move on to the topic molecular symmetry. As the name indicates, the molecular symmetry is the symmetry present in molecules and the classification of molecules according to their symmetry. It is a fundamental concept in chemistry which helps in predicting the chemical properties. Coming to group theory is the systematic discussion of symmetry incorporating mathematical principles, which provides a framework for the study of a molecular symmetry. Let us discuss symmetry and related terms in detail. What is symmetry? An object is said to have symmetry if it can take up two or more spatial orientations that are indistinguishable from each other. Next term is symmetry operation. A symmetry operation is an action which, when performed on an object, yields a new orientation which is indistinguishable from the original. Now, the symmetry element. Well, in our daily life, we might have noticed similarities of a dress, face and hair type of some people. Am I right? If two persons have similar type of curly hair, then with respect to that curly hair, they are similar. That means the curly hair is the element of symmetry there. Likewise, in any object, say it is crystals or molecules, there are symmetry elements with respect to which their symmetry is concerned. Here, a symmetry element is a geometrical entity such as a line, plane or a point with respect to which the symmetry operation may be performed. Now, let us talk about the symmetry of a water molecule. Here, you can see labeled hydrogens HA and HB in the first configuration. If we rotate the molecule in the anti-clockwise direction about z-axis through 180 degree, the new configuration will be similar to that of first. But the hydrogens will be interchanged. HA goes to the place of HB and vice versa. The hydrogens are labeled in order to monitor the action or changes occurred. If the hydrogens are not labeled, we can't identify the original one. The two configurations are now indistinguishable from each other, which confirms the presence of symmetry. You might have surprised about the anti-clockwise direction of rotation. Why is it so? Can't it be clockwise? Well, the people who first worked on this did so. Nothing special about this. Unless and until the direction of rotation is not specified, it is conventionally considered in the anti-clockwise manner. Now, I hope you have understood the concept of symmetry. Alright, let us go deep into the subject. Next, we are going to discuss about the elements of symmetry and the associated symmetry operations. The key aspect of the molecular symmetry is that all the symmetry elements existing for a molecule will pass through a common point which is known as the center of gravity of the molecule. And this point remains unchanged upon carrying out any symmetry operation on the molecule. There are only 5 types of basic operations that leaves this center of gravity of the molecule unmoved or invariant or unchanged. And they are, first one, identity element. It is the symmetry element and the corresponding operation is identity operation represented by E. Second one, center of symmetry or a inversion center. The operation is inversion denoted by I. Third one is plane of symmetry or a mirror plane. The operation is a reflection designated as sigma. The fourth one is proper rotation axis and the operation is proper rotation which is labeled as Cn. And the last one is improper rotation axis and the equivalent operation improper rotation or a roto reflection or otherwise it is called roto inversion symbolized as a Sn. Now, we have to discuss these 5 symmetry elements and the symmetry operations in detail. As of the first, the identity element and its corresponding operation, identity operation. The identity operation is the one in which the molecule remains in its original configuration. It is otherwise called a do-nothing operation that leaves the system unchanged. All the molecules possess identity element. The second is center of symmetry or inversion center I, and the corresponding operation is inversion. An object is said to have an inversion center if the same surface feature is located on exact opposite sides of the crystal and are both equal distance from the center of the crystal. The surface features include points, corners, edges or faces. Here the inversion center is the symmetry element and the inversion through this center creates symmetry on either side. The central point is called the center of symmetry or a center of inversion or otherwise inversion center. It should be noted that a crystal may possess a number of planes or an axis of symmetry, but it can have only one center of symmetry. As you can see in the picture, any line drawn through the origin will find identical features equidistant from the origin on the opposite sides. Example for a center of symmetric molecules are N2, CO2, acetylene, etc. And it is to be noted that in carbon dioxide, the central point is inside the carbon atom. More examples are ethylene, benzene and SF6, that means sulfur hexafluoride. In the case of SF6, the center of symmetry is inside the sulfur atom, not on the periphery. In a plane, we can depict it like that only. The third one we are going to discuss about is axis of symmetry. The operation is proper rotation, denoted by Cn. The proper rotation axis or an axis of symmetry is a line about which the rotation through a certain angle brings the object into an orientation which is indistinguishable from the original, which is also superimposable on it. The axis then is called n-fold proper rotation axis if the angle of rotation is 360 degree divided by n, where n can be 1, 2, 3, 4 and 6. If the equivalent configuration occurs after rotation of 180, 120, 90 and 60 degrees, then the axis of rotations are known as 2-fold, 3-fold, 4-fold and 6-fold axis of symmetry respectively. Let us discuss in detail 1-fold rotation C1. Example for an object having 1-fold rotation axis is a banana. Its two ends are different, right? Either a 0 degree rotation or a 360 degree rotation only can bring indistinguishable configuration. 0 degree and a 360 degree both have a same effect, isn't it? Since this is a do-nothing operation, it can be referred to as an identity operation, E. That is, an object that requires rotation of a full 360 degree in order to restore it to its original appearance has no rotational symmetry. Since it repeats itself one time every 360 degree, it is said to have a 1-fold axis of rotational symmetry. Every molecule has infinite number of a C1 axis. 360 degree rotation around any axis will restore the molecule to its original configuration. Hence, C1 operation is trivial. Trivial means what? It is insignificant. Coming to 2-fold rotation axis, a wooden propeller having 2 ends is an example. If an object appears identical after a rotation of 180 degree, that is twice in a 360 degree rotation, then it is said to have 2-fold rotation axis, that is 360 divided by 180 is equal to 2. 3-fold rotation axis, example is an aluminium propeller having 3 blades. As you can see here, in some war movies and all, you might have noticed aeroplane propellers like this, isn't it? And also in your chemistry lab, there will be propeller exhaust fan. Objects that repeat themselves on a rotation of a 120 degree are said to have a threefold rotational symmetry. 360 divided by 120 is equal to 3, and they will repeat 3 times in a 360 degree rotation. Here the axis we are referring to is an imaginary line that extends towards you perpendicular to the screen. Fourfold proper axis of rotation. Example is an aluminum propeller having 4 blades. If an object repeats itself after 90 degree rotation, then it will repeat 4 times in a 360 degree rotation, as illustrated previously. Now, sixfold rotational axis. If a rotation of a 60 degree about an axis causes the object to repeat itself, then it has a sixfold axis of rotational symmetry, that is 360 divided by 60 equal to 6. Did you notice in between these 4 and 6 I have missed a 5-fold symmetry? Actually it is not a mistake. The crystals do not possess 5-fold symmetry. Although objects themselves may appear to have 5-fold, 7-fold, 8-fold or a higher fold axis of rotational symmetries, these are not possible in crystals. In crystals, the atoms or molecules are internally arranged in a very regular and periodic fashion in a 3-dimensional pattern. And the identical repetition of the unit cell can take place only when we consider 1, 2, 3, 4 and 6-fold axis. We can't pack objects like pentagons or octagons such that they fill up the space entirely. As we can see in the figure, there will be unfilled space or overlaps. Nature doesn't prefer such formation on its own. In nature, we can't see such type of crystals. As science people, we are trying to describe what we see in nature. Now, are you interested in knowing the axis of symmetries of a cube? A cube have 13 axes of symmetries. 3 fourfold axes, that is known as tetrad axis, each of which passing through the centers of 2 opposite faces, as seen in the first figure. And then 4 threefold axes, that is triad axis, each of which passing through 2 opposite vertices, shown in the second figure. And then 6 twofold or a dyad axis, each of which passes through the midpoint of 2 opposite edges, as seen in the third figure. So, 3 plus 4 plus 6, a total of 13 axes of rotation. Let's look for a demonstration. One simple trick to note the axis of symmetry is that look for the corners around the axis. If 4 corners, then it is 4-fold. Now, let us exemplify different proper rotation axes. Firstly, let us look for a 2-fold proper rotation axis C2. A good example for a molecule having C2 axis is water molecule. Water molecule has a 2-fold proper rotation axis, that is C2 in the plane of the molecule passing through the oxygen atom and bisecting the HOH bond angle. A rotation of a molecule through 180 degree about the axis gives the indistinguishable configuration. Coming to the 3-fold proper rotation axis, BF3 is the molecule having C3. One important point is that if a molecule possesses several symmetry axes, then the highest fold proper rotation axis is considered as the principal axis and the others are considered as secondary axis. In BF3 molecule, the axis passing through the boron atom is C3 because 120 degree rotation about the axis in anticlockwise manner yields an orientation equivalent to the original. This is the principal axis of the molecule. Other than this, BF3 possesses 3 secondary C2s also, each one passing through the boron atom and the fluorine atom in the molecular plane. Another example is methane. Methane is a symmetrical tetrahedral molecule that possesses 3 C2s and 4 C3s. To make the point little more clear, the CH4 molecule is embedded in a cube. Here you can see two hydrogens in below plane are diagonally opposite, and the hydrogens on the upper plane are also diagonally opposite, but on the other way around. The central position is occupied by the carbon. In the first picture, you can see 3 C2 axes, each one passing through the central carbon atom and opposite face centers of the cube. How many faces does a cube have? 6 faces, right? Two opposite faces have a 1 C2. Like that, 3 C2s are possible. The rotation through C2, that is 180 degree about the axis, will give rise to indistinguishable configuration. And in the second figure, you can see 4 C3s, each one passing through CH bond. The rotation through C3, that is 120 degree about the axis, will bring an indistinguishable configuration. Both are combined in this figure. See here, C2 is represented in red in color. Likewise, there are 2 more C2s. Hence, a total of 3 C2s are possible. You can see C3 also. C3 is a green in color. Likewise, a total of 4 C3s are present. Which is the principal axis here? As we said earlier, it is the highest order axis. Hence, out of C2 and C3, C3 is considered as the principal axis of methane. Now, let me give you some other examples. Ammonia and CH3Cl. Well, in ammonia, which is a pyramidal molecule, you can see C3 axis, that means a 120 degree rotation about the axis gives the indistinguishable orientation. We can observe symmetry after a rotation of 120, 240 and 360 degrees. The 360 degree is equivalent to 0 degree, right? So, there can be 3 configurations, out of which one configuration is original one and the other 2 are duplicates. In the second figure, you can see CH3Cl, that is chloromethane or a methyl chloride, which is a tetrahedral molecule and it have only 1 C3 like ammonia. Coming to fourfold axis of rotational symmetry, XeF4 is the molecule showing fourfold axis of symmetry. XeF4 is a square planar molecule. It possesses 1 C4 and a 4 C2 axis. The C4 axis passing through the xenon atom and perpendicular to the molecular plane, that is the plane of the molecule. The 4 C2s are in its own plane. 2 of them passing diagonally through the square plane represented by the dotted line, and the other 2 pass bisecting FXeF bond angle. Next is 5-fold proper rotation axis of symmetry. C5. Example is cyclopentadienyl anion. As you can see in the figure, C5 axis is perpendicular to the plane and passing through this center. Also, it has a 5 C2 axis in its own plane, represented in the last figure. Next is 6-fold proper axis of rotation, C6. Benzene is the example. Here, C6 is the principal axis and also it have 6 C2s in its own plane. 3 of them passing through the opposite pairs of corners as in the second figure, and the other 3 bisecting opposite pairs of edges shown in the third figure. Now, the last one in this section we are going to discuss is about C infinity axis. In linear molecules like H2, N2, HCl, C2H2 etc., they have lengthwise C infinity axis, collinear with a molecular plane, about which the molecule can be rotated by any angle, that is at any angle between 0 and 360 degree in any fraction. That means infinity chances are there to get an indistinguishable configuration. Symmetrical linear molecules like H2, N2, Ce2, H2 etc. have C2 symmetry axis also in addition to C infinity, as you can see in the figure. And this is what I wanted to share you in this video, and the rest of the portion will be discussed in the coming session. And what I talked was about the symmetry of the molecules, definition of symmetry, symmetry elements and symmetry operations, and how they are classified. Out of these 5 classifications, 3 of them we have discussed already, that is, first, identity element and its operation, identity operation, second, inversion center and the operation inversion, and the third one is axis of symmetry and its corresponding operation, proper rotation. The rest of the 2 will be discussed in the coming session. Hope you enjoyed the session. Thank you.